Hello, my name is Joshua Taylor, and this is my lab report for Lab 3, Black Hole. Here's our table of contents. The purpose of this lab is to find the mass of a black hole by observing the force it exerts on an orbiting star, and find the initial velocity that allows a spaceship launching from a planet orbiting the black hole to escape the black hole while narrowly missing it. Models used to do so are solely computational with code, and the lab successfully computes the mass of a black hole and generates the desired initial velocity. Some relevant equations and principles. We'll use Newton's second law, which is the net force of a system is equal to its change in momentum over change in time. Rearranged and expanded, that gives us this bulleted equation, the velocity update formula. We'll also be using the position update formula in the code, as well as the force of gravity equation. And that force of gravity equation could be rearranged to find the mass of a black hole. We'll do that later. It's also important to note that the net force on a system can be broken down into the net force in the parallel direction and the net force in the perpendicular direction on the system. And the net force in the parallel direction is the change in momentum or change in time in the parallel direction, the direction of momentum. All right, so we're just going to use computational models. The first one is of a star, which is our system, orbiting a black hole, which is our surrounding, our only surrounding, and that's also the origin. And then the computational model of a spaceship will be used, which is going to be our system, and that spaceship launches off of a planet orbiting a black hole. Those two things are our only surroundings. This lab uses no physical experiment. So we'll go straight to the code. I used the Lab 3 starter codes that were provided. I edited specific lines of code to calculate the gravitational force, including its perpendicular and parallel components acting on the orbiting star. The force values generated a new mass of the black hole at every iteration, so I had to average all mass values to find the true mass value. And I edited specific lines of code in another tab with the second starter code to generate the launch of a spaceship off of a planet orbiting the black hole, being conscious of the forces acting on the ship and the planet. So before we get into this, let's go over the code. Here is the first system. We've got the gravitational constant, the star's mass, which is given. Our delta T for every iteration is 1 day. We're given the initial and final velocities for the first iteration and work from that to get initial and final momentums, change in momentums, separate those into Fnet and Fnet parallel, Fnet perpendicular. And then at the end, we use the rearranged force of gravity equation to find the mass of the black hole. So running this program, all of these are the masses that are generated for every iteration. You can see the force perpendicular is in cyan, the force parallel is in magenta, and the net force is in orange. And so after that orbit, we have all these masses, and I averaged them to get 1.9 times 10 to the 34 kilograms. And then in our second computational system, we take that mass that we found previously and we find the forces acting on a planet orbiting that black hole, find the forces acting on the ship that launches off of the planet, and then we play around and find some velocities that allow the ship to launch off, undergoing all these forces, and narrowly miss the black hole. So this is what I came up with. That's a pretty near miss. And as you can see, those were those near miss velocities or speeds. And here was that black hole mass. Now, what does this all mean? Well, the rate of change of momentum can be found by knowing the mass of an object and observing its change in motion over a given period of time. And then force is the sum of all acting forces. The parallel component is responsible for the change in an object's velocity and momentum, while the perpendicular component is responsible for the change in an object's direction of motion. And overall, they're extremely similar. The net force can be known by observing the rate of change in an object's momentum. What if we wanted the spaceship to orbit the black hole? Well, I found that using this speed in the y direction, the spaceship can orbit the black hole just trailing and surrounding the orbit of the cyan planet. So in conclusion, the mass of an object can be determined by the observed force it exerts on another system. It takes a tremendous amount of speed in the proper direction to escape the gravitational pull of a black hole, even from a considerable distance out. And entering into the orbit of a system is a difficult and precise thing to do. Thanks for watching.